Hello, everybody. My name is Lynn Wilkinson. I'd like to thank you today for joining us on our course on net zero energy and water. And this course is being presented to you by Design Art Seminars, and we thank you for choosing us for your CEU needs. And I want to talk about this idea of net zero. Hopefully, most of you have at least come across this term at some point in time, but you may not be familiar with what it necessarily is. So, what is it when we're talking about net zero energy? At its most basic, the idea of net zero energy is that you produce the same amount of energy that you consume, and that hopefully you're producing that energy from even renewable sources. So, net zero is going to be having an enormous impact on design and what we in the design industry are doing, because the federal net zero energy building goals were set up by Executive Order 13514, and they were signed into being in October of 2009. It's requiring that all new federal buildings that are entering the planning process in 2020 or thereafter be designed to achieve net zero energy by 2030. And so you can imagine the ripples from this are going to be huge, similar to when they passed the Energy Independence Act for the electric light bulbs or lamps. What happened with that is they were going to require that initially they went to a higher energy efficiency and then would finally reach a 200% more energy efficient, which essentially made the incandescent lamp obsolete and really forced the LED into a fast track of adoption, of research and development, of really feasible uses for LED, and really fast track that. So this whole thing of the net zero energy building code for federal buildings is going to have the same impact. The concept of a net zero energy building, or an NZEB, one which produces as much energy as it uses over the course of a year, recently has been evolving from what was purely theoretical and then moved into the world of research and development. It's now actually crossed over into reality. Currently, there are only a small number of highly efficient buildings that meet the criteria to be called net zero. As a result of advances in construction technologies, renewable energy systems, and academic research, creating net zero energy buildings is becoming more and more feasible. And it's a good thing because, like I said, having that federal mandate coming on the horizon is really going to help push this. So make no mistake, net zero has become a reality. The global demand for energy is expected to increase 35% by 2035. And 2035, as y'all know, that's going to be here in a blink of an eye. Many systems that we have will simply not be able to keep up. The idea of rolling brownouts and rolling blackouts is probably going to become very common because there's just going to be too much demand on a centralized municipal power grid system. There's just going to be more demand than they can actually handle. So as the net zero energy and the net zero energy concepts are relatively new, they are not yet definitive, widely accepted zero energy metrics. There's no real, if you want to think of it, just consistent set of guidelines. The Department of Energy, the DOE, and the National Renewable Energy Laboratory, NREL, have spearheaded much of the work on net zero energy buildings to date. And so whether it's understanding emerging trends or troubleshooting or overcoming the technical barriers because we just haven't had the technology to do this, their mission is to provide the support that the building industry is going to need as it continues to evolve into these key areas, and as it intends to just create as we learn more about how this beast can possibly be managed. So the key areas that we're going to be having for this, the key capabilities that you're going to be looking for are data-driven building energy modeling tools, performance mapping and technology evaluation, renewable energy integration, and then moving technologies to market. And so NREL's residential buildings researchers explore energy efficiency options for both new and existing homes, including whole house performance and the interaction of the individual building components. The commercial building team focuses on providing large institutional and private sector commercial building owners with the tools, the resources, and the expertise to address the energy challenges that they're going to be facing. And so NREL has developed uh, several definitions for net zero energy. And so they encourage the building designers, the building's owners and operators. You need to select the metric that fits your project the best. And there's no single metric. That's what I'm saying. You got to find the guideline that's going to work best for what you're trying to achieve with what you're trying to achieve. Okay, so NREL has a publication called Zero Energy Buildings, a critical look at the definition. It's available as a downloadable PDF. It's about 477 kilobytes. And once again, it's Zero Energy Buildings, a critical look at the definition. And what it does is it explores definitions in detail, and it suggests 4 ways in which net zero energy may be defined. First, you have net zero site energy. You also have net zero source energy, net zero energy costs, and net zero energy emissions. So let's take a look at what these 4 different kinds of metrics that could be applied to your project are. Net zero site energy. This refers to the energy consumed and generated at a site, for example, a building, regardless of where or how that energy originated. So in a net zero site energy building, for every unit of energy that the building consumes over a course of a year, it must generate a unit of energy. And this is the most common use of the term of net zero. And again, it doesn't really care necessarily where the energy originates from. It could be from a variety of sources. Now, source energy refers to primary energy needed to extract and deliver energy to a site, including the energy that may be lost or wasted in the process of generation and transmission and distribution. Because when you have something going at an off-site, to get it to the actual building, there's actually a lot of energy that can be wasted in that process, especially if you're dealing with older infrastructure, older wires, and aging systems. There's a lot of waste that can occur in that. So, for example, you may have a coal burning power plant, and they may generate 1 joule of electricity for every 3 joules of energy coal consumed. So, if it's a natural gas site, is used at a site, for every 20 joules consumed, 1 joule may be needed to extract and distribute the gas to the site. That factors into your energy use. So the metrics that they're using for net zero source energy buildings, it accounts for these factors. So though the exact metrics can vary depending on the site and depending on the utility factors, it is accounting for how much energy is used to get that energy to the building itself, all the way from the coal to the natural gas, okay? Now with net zero energy cost, this is perhaps the simplest metric to use. It simply means that the building has an energy utility bill of $0 over the course of a year. In some cases, the building owners or operators may take advantage of selling renewable energy credits from on-site renewable generation. and that can help them get to that zero energy cost. So for example, if they're generating energy on site during the day or during a nice sunny bright day, and they only use 80% of what they consume, then they can sell that renewable energy credit back. Now, on a cloudy day when they may have to use some of the municipal energy, they can use that money. So essentially, they're coming out at a zero energy cost. The other kind you have is net zero energy emission. This is a fourth metric. Now, conventional energy sources, most of them for the most part, result in the emission of carbon dioxide, nitrogen oxides, sulfur dioxides. There is some kind of cost to that as far as they create some form of these emissions. Now, a net zero energy emission building, the metric for this one is either using no energy, which results in any kind of emission, or they offset the emission by exporting emission-free energy, typically from their on-site renewable energy systems, so that they're essentially zeroing out any kinds of emissions. Now, net zero energy building principles, whichever metric you're choosing, can be applied to most types of projects, including residential, industrial, commercial buildings, in both new construction and existing buildings. Now, the NREL South Table Mountain campus in Golden, Colorado consists of over a dozen buildings that have achieved not only LEED certification, but most of them have also achieved net zero energy status and are now being used as models for sustainability. Everything down to even they have xeriscape native plant landscaping so that they can minimize their water usage are part of this thing. So the research support facility building is currently the largest NZEB net zero energy building in the United States. So this is for people that say you can't do net zero energy on a large scale. This is a 220,000 square foot project that achieved the net zero site energy goal through a performance-based design build process. So the design and construction teams work very closely together on this. Numerous energy efficient strategies were implemented, including incorporating advanced heat recovery technologies that were developed and designed by the researchers at the lab, and also installing 1.6 megawatts of photovoltaic power on the campus through a power purchase agreement. Additionally, daylighting, natural ventilation, and a next generation energy efficient data center are among the energy features of this building. If you want to see this building and see this campus in person, highly recommend it. It is open to the public. This is a federal building. These are your tax dollars at work. So if you want to schedule a little road trip on this one, let me know, because this would be a really fun place to go and see in person and actually see these technologies in a functional application and see how you can put a building like this together, even a 220,000 square foot building. So energy resilience. There are three cornerstones of resilient energy. First is you have to be very energy efficient. The less you use, the more resilient you can be because you don't require as much. Secondly, some kind of on-site energy generation from a variety of sources. And number three, some kind of emergency planning. So you need to have some kind of storage, you need to have backup generators, you need a redundant system, because if you've only got one system and it goes down, you're not very resilient. Now, it goes without saying that if you're going to try to live off of the energy that you generate, you need to be frugal in how you're spending that energy that you're generating. So to get to net zero more easily, you need to make sure that the home or the building uses less energy to begin with. Makes it a whole lot easier to get to that goal of net zero. Now we're going to take a little bit about residential here. In 2014, and these are some of the most current verifiable numbers that I could get. Okay, there are some more recent numbers, but I haven't been able to vet them as well. So 2014, the average annual electricity consumption for a U.S. residential utility customer was about 10,932 kilowatt hours, which was an average of 911 kilowatt hours per month. It hasn't gone up that dramatically since then, so we're still basically in that same area. This gives you your basic ballpark. Now, on average, the biggest chunk by far goes to heating and cooling at more than 40% of the electricity consumption. Second highest, water heating, 12%. Next, lighting. That's actually gone down as we've seen more and more LED being incorporated in, but still a significant chunk. And then you get into 17% for things like the refrigerator and other appliances that you may have in the house. So simply by specifying products that are more energy efficient, maybe Energy Star rated, you can have a dramatic impact on the total consumption amount for the house. So things like high energy or high efficiency appliances. Energy Star is a rating system, and they provide energy efficiency ratings on a whole massive slew of things, of equipment. For example, refrigerators, freezers, clothes washers and dryers, dishwashers, water heaters, HVAC equipment, televisions. You're all kind of aware of those probably, but you also have to know that they do windows, doors, skylights, roofing products, even light fixtures and lamps, and more and more and more. Energy Star is actually a U.S. Environmental Protection Agency, EPA, volunteer program. It was actually established in 1992 to help promote energy efficiency products and buildings in order to reduce energy consumption, to improve energy security, because as a nation, energy use definitely impacts the security of the country, because if you are in a fragile state, that you have very high energy demands and you do not necessarily can't guarantee the energy supply, that threatens your energy security. Also, reducing the pollution through voluntary labeling or other forms of communication about the products and about the buildings that meet the highest energy efficiency standards. So they have certifications for all different kinds of things. They have certifications for homes, for buildings, and more than 50 different types of products that are energy efficient and offer the features and performance that today's clients expect. To give you an idea of how much better appliances are than even current federal manufacturing standards, for if you're comparing an Energy Star standard versus the federal standards, for refrigerators, Energy Star, they're at least 15% better than the current standards, and they're 40% better than the 2001 standards. So if you've got a really old refrigerator, you may want to be replacing that because it's probably using more energy than the whole rest of the house. Also, dishwashers, 41% more energy efficient. Clothes washers, 40 to 50% more energy efficient for Energy Star versus current federal. And they use 55% less water, which that is huge. Now, that's Energy Star when we're talking about products. In order to earn the Energy Star label, products must be third-party certified based on testing in EPA recognized labs. So you can't just have a third party certify it. They have to certify it in an EPA recognized laboratory. In addition, they have to have the upfront testing, and a percentage of all Energy Star products are subject to off-the-shelf verification testing each year. And that's huge because the goal of that testing is to ensure that changes or variations in the manufacturing process do not undermine a product's qualification with Energy Star requirements. What happens a lot of times when you're dealing with a product that, yes, the manufacturer is still making model XYZ, and you can still get model XYZ at store ABC, and the XYZ was certified for Energy Star. But what they're going to do is once a year or so, they're going to go and they're going to get that model XYZ off the shelves of store ABC, and they're going to run the testing again. Because what happens is sometimes a manufacturer may no longer be able to get, say, a certain gasket. And so they have to resource that gasket. Well, now, because they're using a different gasket, it could impact the Energy Star rating. It may not be as energy efficient as it was when it was initially tested. So by doing this off the shelf verification ongoing process, you're assuring that they're having to maintain that original standard that they had when the product was Energy Star rated. So that is a very tight level of certification. That's why I'm saying this is a certification that has a lot of respect because of this. The other thing is for a home, a new home. Verification of a home's energy efficiency by a third-party organization is mandatory if you want to earn the Energy Star Home label. And a lot of people are not even aware that Energy Star has a home certification program. Now, in order to do this, if you want to design a house that is going to have the Energy Star rating for the home, there's two different paths that you could take to get that certification. The first one is the prescriptive path, and it is based on a predefined package of improvements, while the performance path is based on a customized package of upgrades that you have to verify meet the performance standards. So the national program requirements define the core energy efficiency specifications for both paths. And so it's not too hard to achieve this. Energy Star rated homes require completion of inspection checklists. Some of those inspection checklists include the thermal enclosure, the HVAC. It has to be 18 SEER or higher for the air conditioning, and the HSF has to be 10 or more for the heating system. And it also looks at the water management. If you're considering doing this, it is definitely worth just at least downloading these checklist requirements. Uh, they've already done the work and standards. If you're just trying to build a house for your product or design a house for your client that is just going to be more energy efficient, you do not need to completely invent the wheel from ground zero. Energy Star has done a lot of that work with you. And all of those checklists and all of those programs and guidelines are available free. So you can download those. They're very good. Particularly their checklist for the thermal enclosure of the building envelope is really worth taking a look at. Now, I said that the lighting was 11% of the home's energy cost. By switching all lighting to more energy efficient technologies, this explosion in LED technologies can have an enormous impact on the energy consumption demand. That 11% for home electricity consumption, and actually for a nation, nationally, it's about the same nationally for all buildings for energy consumption. You can almost, by employing all LED lighting, drop that in half. Now, for an individual home, you may not think that's that huge on the monthly electric bill, 10, 20, 30 bucks, okay. But when you're looking at it as a national average or even as your annual savings, it can be huge. And depending on how you do the strategy for that, it can go as high as an 80% energy savings. Now, that's getting into some real dollars every month and really real dollars at the end of the year. So if you think it's not possible for a house to be all LED, you were right a couple years ago because this is residential. And in residential, there is a certain expectation of the aesthetics. You can't just go pure function. And even, to a degree, a lot of commercial, the aesthetics factor into this. People are not willing to go completely energy efficient if it's ugly. I know I wouldn't either. And so one of the big things that was always a sticking point is the heat sink. And so if you look at the image in the top left, that was that typical type A LED that came out. And that whole big solid opaque white base, that was the heat sink. And the heat sink's point was to pull the heat away, not from the LED chip itself. The LED chip is a silicone chip. It's not affected by heat. So people are like, LED doesn't produce heat. Why is the problem? Why do you need to have a heat pump or heat sink for it? The electronic wires that go through the chip, so the anode and cathode wires, those were where you needed to get the heat away because these were very thin. And so when they first came up with the LED bulbs, lamps, they had that physical heat sink to passively dissipate the heat away from the electronics and extend the life of the lamp. Well, the problem with that is when you got into certain kinds of visible bulbs that you would be using, for example, a candelabra bulb, nothing is uglier than one of those big chandeliers with the exposed candelabra bulbs that they put 30 or 40 candelabra bulbs on that all had heat sinks on them. Now, if you were going for a super, super contemporary, you might be able to pull it off. But if you were doing that traditional, the mini arm brass fixture that you always see in the entry points, it looked god awful. So the invention of the filament LED is what's really gotten to the point now where I can tell you, you can find an LED lamp to replace any kind of LED lamp or any kind of lamp available on the market, including things like candelabra bulbs and Edison bulbs. Because the way they did this, if you look at these images on the bottom right, where's the heat sink? There isn't one, right? You just see the clear glass, no heat sink, and you see what appears to be a filament wire inside, just like an incandescent lamp. And the image on the bottom left shows you what it looks like when it's on. It looks just like an incandescent lamp. Now, if you're not familiar with a filament LED, the way it works is the little LED chips, those little conformal coated, so they look bright canary yellow chips, are glued to a wire which is bent to look like an incandescent filament. And then when you put the electricity through it, when the LED chips emit light, it makes it look like the filament is glowing just like an incandescent lamp. Now, they don't have to have a heat sink because by putting the chips in that kind of array, they can passively dissipate enough of the heat without having to have that extra ceramic heat sink on there. So again, these are fabulous for that Edison looking bulb, that candelabra bulb, or any fixtures where you're exposing the lamp. Now you can get highly efficient candelabra bulbs with warm white light that are dimmable and not ugly. So there goes the last excuse for not specifying 100% LED lighting. Now, to get to structures that can have dramatically lower energy requirements, we need to rethink the entire building envelope even better than before. Now, we started getting a lot better with sustainable building practices, and we've learned a lot through the evolution of green building techniques, but this is ramping it up for a climate that will be very different in the upcoming decades. Combining changes in insulation, in air tightness, penetrations for windows, roofing, along with very high energy efficient appliances and lighting, can get energy consumption of a new home to less than one-fourth that of a standard new home today. That's right. We can build these 70%, 75% or more less energy consumption. Can you imagine as a nation if all of the homes were 75% less energy consumptive? We are talking game changing. This is game changing. So the first thing I want to talk about is air tightness, and specifically using fully adhered membranes. With a fully adhered membrane, you can actually achieve air tightness with a minimum of 1.5 ACH at 50 pascals or less. So 1.5 air changes per hour at 50 pascals unit of pressure. Now, there are several ways to achieve this, but one of the best is to literally wrap the entire structure with a fully adhered membrane. Now, this membrane is the water control layer, it is the air control layer, and the vapor control layer. It needs to be installed so it is continuous, including sealing it to the bottom of the house even. So the OSB or plywood sheathing is going to serve as a vapor throttle, because people, when you sit there and you talk about doing this kind of membrane, the first thought that most people have, especially if you live in a hot and humid climate, is moisture. Oh no, it's going to trap moisture. Oh no, we're going to get mold. Oh no, there's going to be lawsuits. This is a technology that has evolved greatly beyond what you might have initially thought. So you're going to have the plywood or the OSB, and that's your vapor throttle. That's what's going to keep you away from getting mold. And you'll notice in this particular structure, first off, it looks like a house that an 8-year-old drew, that kind of cookie cutter shape. But you'll notice there are no overhangs on the structure. The overhangs are actually added after the membrane. Now, this particular project that we're looking at here that I've used for this case study was built by the Building Science Corporation. Some of you may be familiar with that name. This is Joe Listaburic's group. Some of you may be familiar with his name. Joe Listaburric wrote the book on building for hot and humid climates. And this is a book that's available through the AIA publication system. And it is a fantastic book that looks at all the new building sciences for more challenging climates. And this particular project here is the National Institute of Standards and Technology, the NIST, Net Zero Energy Residential Test Facility in Gaithersburg, Maryland. They actually have built a residential home specifically so they can test things out. And this is in Maryland. If you've ever been to Maryland, you will know that Maryland gets all 4 seasons, and they seem to get the extremes of a lot of them. So this is our kind of Darth Vader house right now. It's all wrapped in the black. The lookout framing can then be added over the top of the membrane. So I have a continuously sealed membrane. You can see in this image here, they're starting to add the little overhangs. And these are a type of almost a snap away overhang. If you are building in an area where you have extreme weather, extreme high wind loads, maybe like hurricanes, one of the things that rips a roof off in a hurricane is because the air gets under the overhang and it snaps the roof off the structure. In this situation, my core building is that little building that looks like it's something like a 4-year-old drew it in crayons. The wind could get under these overhangs, break them away, but the building should maintain its integrity. So not only do I get a good thermal membrane, but it also gives me a little bit more structural flexibility in high wind loads. So that lookout framing can be added over the top of the membrane. The next thing is the insulation. So that's all the little white panels you're seeing. That is rigid insulation board. And so the rigid insulation is then cut to fit inside the open frame cavities of the lookout framing. And then the entire building is covered in continuous layer of insulation. Completely contrary to the way this is kind of the reverse of the way we always built the walls, where we put the insulation on the inside. Well, the problem with that, and you all know this if you've ever had to do energy calculation, is every stud is a thermal gap. And so that greatly diminishes your energy efficiency because you have all of those thermal gaps every time you have structural members. By putting continuous insulation on the exterior of the building, you completely eliminate that. And it makes it a much, much better envelope. Now, if you have created a building that is so tight that you're getting 1.5 air exchanges per hour that you've got this going on, you've got that super tight sealed building, you have to introduce fresh outside air forcibly, or your indoor air quality will become toxic. And this is one of the areas that when we first started to build these super tight envelopes, this is where we messed up because we didn't really understand how to do this. And so if you're going to have this super tight, you have to be able to pull that fresh air in to maintain air quality. Now, there's 2 different mechanisms that you could use for this. You can use an HRV, which is the bottom right, that is a heat recovery ventilation. And you can also use an ERV, which is the top left. That is your energy recovery ventilation systems. And what these will do is, depending on your climate, you pick the one that you're mostly doing, whether you're mostly heating or mostly cooling. What it does is it preconditions the incoming fresh air that you're pulling in by transferring the latent temperature and humidity from the stale exhaust air that's going through the fresh intake air. So, what this process does is it saves energy in heating and cooling, and it reduces the load on the HVAC system. So, for example, an energy recovery ventilation, you're going to want to use that in warmer climates like Florida. It's going to, as you'll see in the image, you've got the fresh air coming from outside, top left corner. And you know that's going to be fairly humid, especially if you are in Florida. Now it's pulling that fresh air inside. In the middle of this ventilation box, there's a little magic that's happening. From the inside, you're pulling the stale air from the inside out. But that stale air inside, you paid a lot of energy to cool it, right? So we're going to take that stale air that is cooled, and inside the middle of this, mix it with the fresh, hot, moist air from outside. That way, what's going to get exhausted will have picked up the heat and the humidity. That gets exhausted. And then coming into the house is air that has already been dried out a little and cooled off a little. So, in other words, you use that energy once to cool it. Now you get to save that energy and reuse a little bit of it again. It's kind of like leftovers, if you want to think of it that way. The meal was good the first time. Sometimes the leftovers are even better. Now with the HRV, which is the one on the bottom right, it's the exact same principle. The difference is, instead of inside of this little box cooling and drying out the air, you're doing the opposite. You're heating and moistening the air before you bring it into the house the rest of the way. So a recovery ventilation system is used to recover the energy by sucking that energy back out and using it to temper the air, the fresh air that's coming in. Now, otherwise, that energy would have been completely lost. So that's 100% write-off. If all you do is bring it in and throw it out, it's 100% energy lost. If you're using a recovery ventilation system, you can reuse 80% of that energy again. That is huge. How do you like to be able to reuse 80% of your air conditioning energy? So the system also ensures consistent, superior air quality as an added benefit, with very consistent relative humidity levels in that sweet spot, that 40 to 50%, which is the area that you want to have it for healthy indoor air quality. So not only do you get 80% of your energy that you can reuse, you get a much higher indoor air quality as well. Now, one of the biggest challenges when you're trying to build your thermal envelopes is also the insulation. And this is the question: how much do I use? Where should it go? What kind of insulation should I use? Myriad questions, as you can imagine. Now, the standard residential construction in most of the country is 2x4 wood framing with fiberglass insulation bats, which achieves a whopping R10 for your walls. So you get an R10 insulation value. If insulation is installed at all on the foundation walls, it's rarely more than an inch thick, and insulation is almost never put under the slabs. Now, some states, for example, Vermont, started to require developers improve energy performance, and that led to a widespread switch to 2x6 framing in home building. And we're seeing that continuing. A lot of production builders, they're incorporating the 2x6 framing. But 2x6 wall construction is still fairly inadequate. A well-built 2x6 frame wall insulated with dense packed cellulose or fiberglass bat is still only going to achieve about an R17 or an R18, accounting for that thermal bridging, the thermal breaks through the conductive wood studs. It's hard to get a higher R value because you have so many thermal breaks. So if we want to have a chance of achieving carbon emission reduction goals that the climate scientists are all telling us are going to be needed, They're actually wanting a 80% reduction by 2050 or sooner. We have to start insulating houses much better. We have to start insulating houses differently and thinking about it differently. So, what is a reasonable target that we should now be aiming for when it comes to insulating? I hope you're sitting down. Okay, this is your rule of thumb. We used to think that 2x6 walls insulated with fiberglass or cellulose were perfectly adequate to that relative R value, even defining that house as energy efficient compared to standard construction with a poorly insulated 2x4 wall. So yeah, but that was also when oil was 12 bucks a barrel that we said that that was an energy efficient wall. It takes a lot more insulation and in different places to achieve the level of resilience needed to ensure that the house is going to maintain livable conditions without supplemental heat or electricity, or with very little supplemental heat or electricity. So the new standard rule of thumb for insulation is 10, 20, 40, 60. Remember 10, 20, 40, 60. And that is you're going to have R10 under the concrete slab, R20 in the foundation walls. I have a friend of mine who's an HVAC engineer in Florida. This is when he started to get shaky, is when I said R40 and above grade house walls. And I completely lost him when I said R60 for the ceiling or the roof. Can't be done, can't be done. I will prove to you it can be done. And there are numerous buildings now that are doing it. So new rigid insulation materials applied to the exterior. First off, they eliminate all that thermal bridging, all of those voids from the structural framing. That's a big benefit. There are a variety of products, everything from foil-faced polyiso to XPS to EPS to rock wool. It is a matter of specifying what you think is best for your project. So some true sustainable purists do not like to use any of the rigid foam because the rigid foam is a derivation from the petroleum industry. And if you're trying to go completely petrochemical free and oil free, that is a byproduct of oil production. But they don't conduct any moisture, which is could be a nice benefit depending on what you're trying to achieve. For those who are completely opposed to using any of these kinds of petroleum products, the rock wool rigid boards would be pretty much your only choice. Amongst those, Roxul, ROXUL, was kind of the one that has these full rigid boards. It used to be rock wool was just kind of that loose felty type thing. Now these are actually pressed rigid boards. What you're looking at some of the values, the polyisocyanurate, 4-inch thick, will give you an R24, extruded polystyrene, the XPS, get a 5-inch thick, R25, expanded polystyrene, the EPS, 6 inches thick, R23, and a rock wool 6 inches thick is an R24. So these are all fairly comparable, as you can see, and considerably better than just doing bats in a 2x6. Now, this type of wall construction that we've been talking about, where you've got that reverse exterior insulation, is what's becoming known as the perfect wall. The Building Science Corporation, Joe Listerburek's group, has come up with these basics, but the concept of putting an enclosure together like this was actually figured out a long time ago, mostly by people living in extremely cold climates like Canada and Norway. So the perfect wall is what's diagrammed here. You have 1x6 pine studs, 24-inch on center. You have 1/2-inch OSB sheathing. Then you're going to do that continuous adhered membrane. In this particular case, we're using the Carlisle 40 mil peel and stick, and it is your air, water, and vapor barrier. Then we're going to do 2 layers of 1.5-inch foil-faced polyiso rigid insulation boards, do a 1x4 pressure-treated lath rain screen, and then the siding. In this case, this image is showing corrugated metal. Could be any of the cementitious products, a lot of different choices for siding. So an advantage of having the continuous insulation on the exterior primarily is you have continuous insulation. no breaks for the studs. This method of wall construction allows you to think about the interior finish out very differently because you don't have to insulate the stud cavities. Heck, you don't even have to cover the studs. So the continuous insulation is actually applied over the sealed membrane, including the roof. So remember, we had that black box house, and then we put the lookout framing for all the overhangs. And then we started putting the rigid insulation board continuously around it. You're going to tape all the seams so that you have a tight seal, and that's including the roof. So all the sides of this will be wrapped. And then you can see it a little better in the image on the bottom right that you have weather resistant lathing strips that you're going to screw straight through the insulation and into the supporting OSB and give you the lathing strips on there. These are all sealed holes as well, and then you'll put your cladding over that. It's a pretty straightforward installation here. Now, remember I said this allows you to get a lot more freedom in how you address the interior finish out as well. For example, take a look at this house. The only reason you put sheetrock up is to cover all the insulation in the cavities half the time. So in this particular design, this was designed by Rouser Design. It was built by Risinger Homes in East Austin, Texas. And so when I say we have actual case studies of these things in extreme climates, and if y'all don't think there's an extreme climate in Austin, Texas, I challenge you to come here when it's 105 degrees and we have 85% humidity, and that does happen. And so this kind of thing, you can actually leave all of that open. This is a very different aesthetic look than you could achieve with a traditional house construction, and you have a much better thermal envelope for this entire structure. Their electric bill is almost free for this one. They can go pretty much off grid, even though they're in the municipal center. Now, the other thing are structural insulated panels. And structural insulated panels, most of you have probably heard them, they're called SIPs boards. This is actually a composite building material. It consists of an insulating layer of rigid core sandwiched between two layers of structural board. So they're most commonly made of OSB panels sandwiched around a foam core. Now, foam, there's two different kinds of foam. You've got the expanded polystyrene, EPS. You also have the extruded polystyrene, XPS, or rigid polyurethane foams. Other materials that can be used instead of OSB, you can use plywood, pressure treated plywood for below grade foundation walls. You can have them with steel cladding, aluminum cladding, cement board like a Hardy-Backer board, and even more exotic and costly materials like stainless steel or fiber reinforced plastics or magnesium oxides. Some of the SIPs that use these fiber cement or plywood sheets for the panels and agricultural fiber such as wheat straw for the core. So depending on how green you need to be the product to be, SIPs has some really good alternatives out there. The third component in SIPs is the spline or the connector piece between the panels, because remember, we're trying to go for no thermal bridging. So dimensional lumber is commonly used, but it creates a thermal bridge and it lowers the overall insulation value. To maintain that higher insulation value through the spline, the manufacturers are now making available insulated lumber or composite splines or mechanical locks or overlapping OSB panels or a variety of other really creative approaches that you need to be able to snap these panels together at the same time, not creating a thermal bridge from whatever is being used to lock these together. The other kind of wall structure that you may want to consider for your envelope, most brands of insulated concrete forms, or ICFs, consist of two parallel panels of foam held apart by rigid plastic spacers. Now, the builders stack the ICFs. If you've ever been involved with one of these types of projects or been on a job site where they're using ICF, it's kind of like a gigantic Lego assembly. So they stack the ICFs like Lego blocks, and then they brace those forms, and they've got the rebar running through the interiors of them, and then they fill the forms with concrete straight out of a pumper truck. Now, the ICFs are left in place as a permanent part of the building. So don't think of this as a form, you pour the concrete and remove the form. These stay as a permanent part of the building. They are becoming more and more common, particularly in Florida. Among the advantages over conventional wood framing or even metal framing, very, very low air infiltration, extremely high thermal mass, incredibly strong and fire resistant, very good sound deadening qualities, and much higher insulating values than especially a standard masonry like CMU construction. They can be used to form the basement walls alone or for the entire wall system, including all of the above grade walls. Now, from the foundation to the roof, these are also an excellent construction method. ICFs are airtight, and the layers of polystyrene enveloping 6 inches of reinforced concrete for an extremely strong, durable home with very high insulating properties. This is a type of construction, especially if you're dealing with areas where you're could be coastal areas with hurricane exposure. We're finding some of these ICF homes are withstanding incredibly strong storms very, very well. The core remains intact. You may lose some of the patios and things like that that are additional too, but the core structure is very strong. So composite building materials, let's take a look at some of their comparisons with that. And these are minimal R values. I have seen them with much, much, much higher ones, but I'm trying to go on the conservative end in this presentation to you. So you all know concrete has virtually no insulating value. It's got an R value of about 0.08 per inch of concrete. As a result, the R value with the ICF, it actually depends on the thickness of the foam. So they can range from an R12 and up. Instead, they rely on the thermal mass to add to the energy saving. That's where concrete is good with thermal massing. And that can vary upon the location depending on the weather. So for example, Minneapolis and Chicago achieve much less of a thermal mass than Phoenix or Bakersfield, California. So the performance R value can vary dramatically depending on the region. No surprise there, right? So in some instances, builders have added additional continuous rigid insulation to the exterior of an ICF building to boost the R value even further. So both of these materials do eliminate thermal bridges as they are a continuous insulated material. But you better make sure you've got all your conduits for your electrical before that concrete truck pulls up. You want to make sure you have all your plumbing and all your electrical, your conduits, everything in those forms before you start pouring, because it is very difficult to change window penetrations or as you imagine anything in those cavities. Almost impossible. Now, windows are one of the thermal issues. Everybody loves a window, not necessarily heat gain from it. Typically with windows, R5 is the minimum to look for, but some companies are really starting to go beyond. They're really re-looking at the window. High efficiency windows include well-built, air-sealed windows with good thermal performance. Not great, but good. Typically, what you're looking at is a double glazed or triple glazed window with insulating gas between the panes, usually argon or krypton, and a low E or low emissivity coating. And that's what you get to be considered a high efficiency window. And high efficiency, if you've got an old house with double hung windows with counterweights, an air leak, and a single pane of glass, that is a light year ahead of that. Now, that low emissivity coating, the low E coating, is what's preventing the radiant heat from crossing the window plane. For example, it keeps the heat inside in the winter, but outside in the summer. Now, the framing material is as, if not more important than the glass. Framing materials like fiberglass and wood have very low rates of thermal energy transmission when you compare them to aluminum or PVC, vinyl. Those consistently have some of the highest negative environmental and health impacts according to the life cycle assessment techniques from the United States Green Building Council. So another significant energy pathway is the porosity of the construction, including the ceiling. Uh, Ceiling, C-E-A-L-I-N-G, or S-E-A-L-I-N-G, not the ceiling above your head. Insulation is an important consideration for high efficiency windows. Sirius Energy is the only company so far that I've come across. If you know of another one, please send that information to me, that uses both a combination of low E coatings on the glass and suspended low E film between the glass, and then they use xenon as the gas fill, which is even better than krypton. This achieves an industry-leading unit insulation R value of R13 for a window. So this window uses low iron glass to achieve a very high visible light transmittance of 62% and that efficient of an energy window. So what does it all mean? Well, when you're dealing with windows and glazing, there's a whole soup of alphabet soup out there. A lot of things that are thrown around as terms, and some of them are kind of doublespeak. So you've got low E, U factor, the solar heat gain coefficient, SHGC, and the visible light transmittance, the VLT. So low E windows have a microscopically thin coating to lower the U factor, or in other words, its ability to transfer heat. A low E coating can reduce the energy flow 30 to 50%. Just this coating, 30% to 50% reduced energy flowing through that window, usually in the form of heat. So what is the difference between U factor and R value? And this is always the problem. Everything else that has anything to do with insulation uses an R value rating, except windows. They use a U factor rating. So the U factor is used to express the insulation value of a window. R value is for everything else. So how do I do an apples to apples if I'm trying to do my overall energy consumption and my overall energy rating for the entire structure? Very simple. Math, my favorite thing, right? So to compare R value and U factor, all you have to do is divide 1 by the U factor number. So for example, you have a 0.25 U factor. 0.25 goes into 1 how many times? This is even math that I can handle. Goes in 4 times. Therefore, it has an R4 rating. If you've got a 0.20 U factor rating, 0.2 goes into 1 5 times. You got an R5 rating. So in other words, it's kind of opposite. You have to stretch your brain a little bit. The higher the U value, the lower the R value. So these are in opposition to each other. So just remember, opposite, high U factor, ugly. U for ugly, the higher it goes, not good. Now, in the past, the recommendation was that in northern climates, windows with a higher U factor, which meant a lower R value, a lower insulation level, but with a higher solar heat gain coefficient, were better because they allowed for using thermal mass to store heat for the structure. Now, in southern climates, a product with a lower U factor, which had a higher R value or higher insulating value, and a lower solar heat gain coefficient was more desirable because it would decrease the thermal heat. So for example, up north, if you look at the image on the left, you'll have a U factor of 0.3, which gives you a relatively low insulating R value of 3.33. A solar heat gain coefficient, so how much of the solar heat is transmitted through, could be 71%. And then the visible light transmittance, or VT, sometimes BLT or VT, was 75% of visible light was transmitted. Now down south, You wanted to do the U factor, lower U factor, so that you could have an R4 insulating value, higher insulating value. You also wanted to drop the solar heat gain because that's what was heating up our insides down to about 39%. And then you're also giving up a little bit of the visible light coming through in order to reduce that heat. Now, there's a whole new kind of thinking, regardless of the location. So, regardless of the geographic location, the new thinking is starting to lean towards maximum R value. Insulate the ever loving bejesus out of it, regardless of the location. And the thinking is that having a super high R value envelope for the entire structure and using the HVAC, very energy efficient HVAC, to control the climate artificially is actually more efficient, more energy efficient in the long run. So designers are starting to play with using low U values, which is the high R value for windows, especially on western and southern exposures, and using the high U value on the northern and eastern walls. And there's a lot of controversy on what is optimal for each climate. So one note for the difference between net zero energy goals and resilient energy goals: sometimes their objectives may not perfectly line up. So, for example, with net zero energy, you want to have an extremely efficient envelope, and you can keep the climate controlled with very little energy because of that. But you know this, even with a high energy window, every time you punk a hole in a wall, you're reducing the efficiency of your envelope. So, net zero doesn't want you to have windows, but resilient design says you may still run out of energy production, so you need to have a building with operable windows to take advantage of passive cooling. So this is where there needs to be a little bit of latitude in your overall scope of what you're trying to achieve. And so where are the priorities placed? If you want to have windows for aesthetics, look at where you're placing those windows so that you can minimize the impact as much as possible. Now, the other part of your envelope is the roof. And when it comes to the roof, getting an R60 will give you unbelievable returns. And believe me, this is where I lost my friend who's the mechanical engineer who designs cooling systems in Southeast Florida. He's like, R60, not going to happen. And when I showed him this, he actually had to eat his words and go, okay, it is happening. You can make it work. So for example, with exterior foam, 1/3 of the R value, 20, goes on the outside. So rigid exterior foam insulation boards, you get an R20. And 2/3 of the R value on the inside can come from using a combination of spray foam as well as blown or insulated batt material. But the actual roofing is where you can also make enormous differences. These are the so-called cool roofs, and they have two important surface properties: a very high solar reflectance, or they're also referred to as albedo, and they also have a very high thermal emittance. So it's the ability to radiate heat away from the structure even after it's been absorbed. So most cool roof applications have a smooth, bright white surface to reflect the heat, reduce the heat transfer into the building's interior, and to save on the air conditioning costs and the energy. During a peak summer month, a high reflectance roof can remain up to 70 degrees cooler than a traditional roof. A traditional roof can actually reach temperatures of 190 degrees. If you don't have a skillet, you can go fry your eggs on your roof. So high albedo materials reflect the sunlight. They limit the amount of heat gained through the materials, and high albedo roofing materials are chosen to reduce unwanted heating of the roof surface and the attic and the top floor spaces, which helps to decrease the cooling loads during the summer days. High albedo roofing is known to have a much higher lifespan and also plays a major role in reducing the urban heat island effect. Metal roofing is great, but you want to stick to the natural or lighter colors that have that higher reflectance. For resilience, look for the roofing material impact class rating using the Underwriter Laboratory UL 2218 hail resistance testing standards. Remember, class 4 is the best for this standard. Class 1 is the poorest for this standard. So the material you use, like a standing seam metal, huge difference in heat gain. Another kind of cool roof is a green roof. While not as reflective, green roof systems, also known as living roofs, refer to the partial or complete covering of a building's roof with well-selected vegetation planted in a suitable growing medium spread out over root barrier and drainage layers installed over the roof's waterproof membrane. So automated irrigation systems can also be integrated for ease of maintenance, and these can be used to filter the gray water or harvested rainwater. So you don't have to use first time great fresh potable water. This is a perfect application for that. Green roofs contribute to the reduction of the urban heat island effect. They also contribute to stormwater retention, rainwater filtration, roof membrane protection, and to keep a building cool through evapotranspiration. And they stand up very well to extreme weather like high hail or other kinds of impact. You may have to replant your roof. Your tomatoes and corn and beans may get smashed, but the roof itself will do a much better job of standing up to these weather extremes. So the other type of thing is when we're looking at net zero, you have passive energy and active energy. And so net zero passive energy, some examples of passive energy are solar orientation, shading, daylighting, thermal mass, and natural ventilation and prevailing winds. Solar orientation, most of us are familiar with this one. It's how the house is oriented to the sun, and it can have a dramatic impact on heating and cooling costs. The goal is to maximize natural daylight year-round and gain heat only when desired. So to do this, the home should be longer from east to west than they are from north to south. In fact, the U.S. Green Building Council recommends that the longer east-west axis be a minimum of 1.5 times longer than the north-south axis. So furthermore, the longer axis should not be more than 15 degrees off of the geographical east-west axis. So things like roof overhangs, louvers, trees, these are all commonly used to block direct sunlight in the summer months when it would be over the heat of the home. Now, placing the majority of the windows on the southern wall and orienting the primary rooms like the great room maximize that sunlight to naturally light the space and reduce the need for electric lighting. Northern rooms are going to have the least natural light and make the least sense to put breaks in the thermal envelope, for example, the windows. Laying out the space so that bathrooms, utility rooms, closets, for western rooms, they're going to get full blazing sun as it sets. If the windows are placed here, make sure that you're either incorporating shading or you're putting the highest RValue windows that you possibly can there. So that makes a big difference. Now, when you're talking about shading, either use by design or use Mother Nature to incorporate shading, particularly in southern climates. You want to shade the roof, the western exposure, and as many of the windows as possible to greatly improve the quality of life for the inhabitants, especially what if there's an event and there is no air conditioning in the middle of summer, like after a hurricane. So if you want to know what that's like, how fun it is to live in a non-air conditioned house in South Florida with 2 weeks of no electricity after a hurricane in August and no electric fans, it is a very special joy that once you experience that, you never quite forget it, do you? So by adding shading panels, you can greatly reduce the solar heat gain of the structure. Now, if those panels are able to cool the air before it enters the building, you're using the same natural cooling that was incorporated into buildings long before the use of electricity and electric cooling. So you get a lot of bang for the buck. Now, if you made those solar panels as the shade structure like these on the bottom right. So what if those Bahama shutters were actually solar panel shutters? You can get things like that, that you can secure them during an event. So during a weather event, you secure them, they protect the window, and then they pop back up and can turn into electric production after the event. So taking advantage of trees and plants can also make a difference. And I note that if you are planning for shading to withstand events like hurricanes, you are dealing with some structural considerations, material selections, and also wind shearing also need to be factored in. If the structures can be collapsed and secured against the side of the building or stored during the storm, that can play as a major factor in your design. So for example, the image on the left, you can pull that canvas in and greatly reduce the wind load on that patio there. Mangroves, they're tough, they're low, they're deeply rooted. They're going to withstand very well. When you're looking at the natural plants, look at plants. One of the reasons palm trees do well in Florida is because they bend. Mangroves, tough and dense. Oak trees, live oak trees, pecan trees, mostly you just end up with a lot of broken trees and not a lot of shading after a storm. Proper window shading is going to allow for optimal solar heat gain in the winter while limiting the unwanted solar heat gain during the summer. And so a correctly sized roof overhang is going to completely shade a window at solar noon on August 21st, the warmest and sunniest month of the year in the Northern Hemisphere. Windows that face east or west are going to require larger overhangs or vertically mounted shading devices to complete that shading. Shading the windows from the summer sun is going to help to maintain much more comfortable conditions inside a building, as well as to considerably lower the annual cooling costs and lower the energy requirements. So one thing to note, while the big overhangs in this image, for example, are great for shading, this is not a roof that has a high probability of surviving a high wind event unless you built it with lookout framing and snap away edges. So you have to look at the overall, not just resilience, not just lower energy, but structural integrity as well. Now, daylighting is the practice of placing windows or other openings and reflective surfaces so that during the day, natural light provides effective internal lighting. If buildings have proper daylighting, you can dramatically reduce the need for electric lighting, making them both closer to net zero energy and more resilient. Bang for the buck, right? So when it comes to daylighting, you're looking at mostly windows, combinations of these kinds of things. So windows, clerestory windows, also light shelves, skylights, and solar tubes. Now, windows are the most common way to admit daylight into a space. This is your no-brainer. Now, if you're smart and strategic in your design, you can also use them to achieve goals beyond providing natural light. So for example, take a look at this project. The rows of casement pivot windows open to create a sleeping porch, basically. It's designed so that you've got the left hinge windows on one side and the right hinge on the other, so that they open to capture the prevailing breezes and make that room incredibly comfortable. And it's almost like sleeping on a sleeping porch or in a tree house. After an event, if you have limited power, or if there's a massive power interruption, being able to funnel the prevailing winds to naturally ventilate an interior space would be much more comfortable and much more resilient. Now, historically, clerestory windows denote the upper level of a Roman basilica or the nave of a Romanesque or Gothic church. The walls, which rise above the roof lines of the lower aisles and then are pierced with windows. Today, when we're talking about clerestory windows, typically we're talking about any row of windows above eye level that allow light into a space. So in modern architecture, clerestories provide light without the distractions of a view or compromising privacy when you have housing that is tightly grouped together, for example. They can also be used to provide natural ventilation when used as heat chimney releases. So for example, if you have the cool air coming in, look at the image on your lower right, the cool air coming in on one side of the building, as it blows through the building and through the heat cavities in the upper areas, you can use the clerestory to create ventilation and to create that natural ventilation flow so that you're optimizing the air cooling effect. Now, clerestory windows can also be placed to add natural light in areas that you otherwise may not be able to receive natural light, or it doesn't make sense to put a window there. And so by being high up, they can also be protected from too much sun because of the overhanging eaves. So they can work well in rooms that would receive too much sun otherwise, like a western facing room. You put a higher clerestory, you can still get some natural light, but you're saved from a lot of that heat gain. A light shelf is an architectural element that allows daylight to penetrate much more deeply into a building. Now, if you have done a lot of commercial architecture, you've probably used light shelves, typically on the exterior of the building. So, for example, a horizontal light reflecting overhang is placed above eye level and it has a very high reflectance coating on the upper surface. That surface is then used to reflect and bounce that daylighting onto the ceiling, and then it reflects off of the ceiling indirectly and penetrates much deeper to the interior space than is possible with just windows. Light shelves make it possible for daylight to penetrate the space up to 2.5 times the distance between the floor and the top of the window. So go from your finished floor to your top of your window and multiply that by 2.5 times. You can actually get natural light that much further in the space. With some of the advanced light shelf technology, you can make that number 4 times the distance. So not only do light shelves allow light to penetrate through the building, they're also designed to shade near the windows because of the overhang of the shelf when you're talking about an exterior light shelf, which helps reduce glare. Now, exterior shelves are generally more effective shading devices than interior shelves. However, if it is a very intense sun situation, like a western facing wall, they may actually create too much heat gain. So in those areas, take a look at the image on the right. These are using louvered panels in the upper tier. So the second floor windows have louvered panels as their light shelves. So it doesn't get as much heat gain coming inside in that western facing. So right product, right application. I think I'm going to have that tattooed on me because I say it all the time. Now, light shelves can also be effective indoor as well. Plus, you don't have to be as considerate with them. You don't have to worry about them being destroyed in high winds or in a storm, for example. Now, if you use a paint with a high light reflectance value, you can almost triple the amount of light that can be brought in. And then that light is also low glare, indirect light, which from a lighting design perspective is what we're always trying to achieve, reducing the amount of glare. That's our optimal goal. So note here the incorporation of the light shelf above the window. So look on the left side, you see the light shelf above the window. It's not just a little soffit fur down. People think, okay, it's a dust bunny ledge, it's a plant ledge. It's not just a plant ledge. By having that clerestory window there, and then the top of that is coated with a high reflectance paint, that is an interior light shelf. And it's incorporated into the interior design by keeping that horizontal line with the soffit over the kitchen area. So you've got a light shelf, and then a soffit, and it's creating that lovely horizontal banded rhythm within the space. So it's function first, and then aesthetics and form second. Now, the winning combination is to combine the light shelf, whether they're exterior or interior, with clerestory windows. You can create a great deal of deeply penetrating light with a lot less glare, and because the windows are going to be more shaded by the overhang, a lot less heat coming through that space, and also good privacy. The other way to do daylighting is through skylights, and skylights have come a long way. They are much more energy efficient with low E glass, and they come with sealed collars for virtually a foolproof insulation, if you want to think of it that way. Now, large skylights can compromise the thermal envelope, and they're not as resilient from impact events like hail. There are other types of things out now, like solar tube products, that are a great way to light a small room for closets, hallways, pantries, bathrooms. And they even come with the option to have an LED lamp inside the tube so that they can be used at night as well. Now, these are actually able to reflect moonlight and starlight really, really well. And so when we first started to put these kind of tubes in, we had to be mindful that they actually went back and re-engineered them, that they have a baffle in them so that you can turn them off, because people were complaining you put this in their master bathroom and it was so much light coming through at night, especially with a full moon, it was keeping them awake in the master bedroom. So look at the options available in these kind of products and make sure you're specifying correctly. Now, it is still a penetration in the envelope, but they have some very low profile ones, and it's a much smaller penetration. So that can help keep your energy efficiency in your envelope. Now, solar tubes, the inside is also getting a little bit more fashionable. Uh, Instead of just that frosted lens, that 10, 12, 14, 16-inch frosted lens, they're actually making the lenses for these integrated into what looks like a surface mounted light fixture. The one on the upper left is obviously the European company, and the other three are the American companies, but they look a lot better than they did as far as improving the aesthetics. The other passive energy is thermal massing. Now, this is using a material's resistance to change in temperature. Objects with a high thermal mass absorb and then retain that heat. And locations where you have a huge temperature swing from day to night, for example, desert climates, thermal massing is always used to aid passive solar heat design. Thermal mass can store the energy absorbed from the sun and then slowly release it over time. Conversely, it can resist heating up too fast from solar radiation. So it means that instead of the first couple millimeters of a wall heating up 5 or 10 degrees, the entire wall only heats up 1 to 2 degrees. So objects with a high thermal mass, for example, concrete, absorb and retain the heat. It's slowing the rate at which the sun heats a space and the rate at which a space loses heat when the sun is gone. Without thermal mass, heat that has entered a space will simply re-radiate back out quickly, making the space overly hot with sunlight and overly cold without it. Thermal mass, however, is not a substitute for insulation. I'm going to cause a war right now, because there is a major shift in thought that is gaining a lot of ground when it comes to the value of thermal mass. Yes, in areas, parts of the world where you have these high temperature swings, this has been what's been done throughout the ages. This is now coming into study that it no longer is the correct way to build. In fact, more and more studies are starting to downgrade thermal mass when you compare it to super efficient insulation. The insulation materials and methods that we have today are starting to provide far superior to what could be achieved using thermal mass. And so this may become the building method of the past, where the newer insulation materials are now becoming the pathway to the future. So a lot of argument in this field. Boy, you talk about this in Santa Fe and you just open up a can of worms. But there's a lot of study that's proving that this may be a type of architectural design that is going into history. The other thing is passive energy using prevailing winds. And prevailing winds are the winds that blow predominantly from a single general direction over a particular point. It may change from time to time, but usually the wind always goes that direction. Now, wind ventilation is a kind of passive ventilation that uses the force of the wind to pull the air through the building. It is the easiest, most common, and often the least expensive form of passive cooling and ventilation that you can use. Now, strategies for wind ventilation include operable windows, all types, whether they're casement, double hung, clerestory, awning. That also includes ventilation louvers and rooftop vents, as well as using the structure itself to funnel the wind, to create that. So windrows diagrams can be used to determine what the local winds are. If you ever want to look into this, look up the windrows diagrams, whether they are a strong prevailing wind to whether it's a seasonal prevailing wind to whether you have a situation with variable breezes. Now, designing a building that can take advantage of summer breezes for passive cooling, as well as shield against adverse winds that can further chill the interior on an already cold day, or even prevent snow from piling up against the windows and the doors. So just remember that prevailing winds can destroy a building when they're whipped up in that 200-mile-per-hour event. You don't want to be funneling 200-mile-per-hour wind through your structure. So yes, factor in the prevailing winds to your design as a way to reduce energy use, add comfort, and after an event when there may not be power, it'd be great to have this. But place them strategically or add some method to shield them during an event so that the building is more resilient. So take a look at this beautiful home. It has the brilliant design of a heat chimney. And if you've ever been deep parts of the South, this was actually a remarkable achievement. And so what happens is the top of the chimney, in this case, is the cupola. Most likely in a high wind event, that's probably not going to survive a storm. So how would you design a heat chimney that would allow the wind to flow around it and remain attached to the structure during a wind event? But during the other times, you could have this wonderful central heat chimney core where the air comes through the house and funnels up through that, creating wonderful cooling effect. What would that look like? I'm curious. If you come up with a really revolutionary one, send it to me. I'll share it with others. Now, active energy can come from a variety of sources. All the ones we've been talking about so far, thermal massing, prevailing winds, solar, that's all passive. Now, active energy, excuse me, not solar, active energy is using some form of mechanical and electrical equipment to convert the energy into power. So, for example, to achieve net zero active energy, you are dealing with primarily four different types of potential equipment: photovoltaic, solar, solar thermal, geothermal, and wind. In some interpretations and guidelines, part of being net zero is to also have dramatically reduced carbon dioxide emissions, CO2 emissions. So as you all know, burning fossil fuels creates a great deal of carbon dioxide, which could negatively impact the atmosphere. Further, fossil fuels are not renewable. Once we have consumed what is on or in planet Earth, that's it. We're done. We can't keep taking and taking. It is a finite resource. So whether they are easily subject to interruptions, which we might see, for example, with oil, if the supplier wants to stop supplying, you're out of luck. The other non-renewable energy source is uranium, which is used in nuclear energy. Now, nuclear energy does not produce carbon dioxide. It does, however, have a couple of drawbacks. Chernobyl comes to mind, as well as 3 Mile Island, as well as the most recent Fukushima. Now, ideally, for true net zero energy, those sources need to be eliminated, and renewable, non-carbon dioxide, non-radioactive sources should be your focus. Now, we do have finite energy sources. We are fortunate to have renewable, virtually infinite sources as well. So you've got finite fossil fuels and uranium, but we have infinite other sources. We are getting better at using them, and we are getting more efficient with them. So some of these are solar energy, energy from the sun; wind energy, energy from air movement; geothermal energy, which is the heat energy from the earth itself; and hydro energy, energy from moving water. They are plentiful and they are renewable. We just need to keep improving how we can more efficiently capture the energy they yield and store that energy. So of those, solar, wind, and geothermal can be used for individual structures relatively easily, depending on the density for the location of the structures. Hydro energy is generated usually by dams or tidal generators, offshore tidal generators, and it's really only applicable for a large utility company or municipal utility company to use as an energy source. It's not really practical for one individual use. Now, solar energy. Our sun. How hot is our sun? If I said, how hot is the sun at its core? Fahrenheit degrees. How hot do you think it is? Now, right now, it's about 100 degrees in Texas. That's hot enough for me. The interior core of our sun is 27 million degrees Fahrenheit. In 1 second, so 1 Mississippi, just then, the sun produced enough energy equivalent to what we would use at current global consumption levels for 500,000 years. That is a pretty good little generator. Now, we may not be able to achieve that level of energy production here on Earth, but our friend, the sun, can help us create at least some energy here using solar or photovoltaic panels. Now, as a method of converting solar energy into direct current, DC, electricity, the direct conversion of sunlight to electricity occurs without any moving parts or environmental emissions during the operation. At its simplest, the light from the sun hits the solar panels, which are composed of a number of solar cells that contain photovoltaic material. The panels are attached with copper wires and they produce DC current, direct current. Because most homes use AC, alternating current, usually there is an inverter to convert the current from DC to AC, and then the electricity can be used by the home. Now, there's a few different paths to the actual electricity that paths that the actual electricity can take. You can have grid tie, off grid, and grid with storage. So let's take a look at these. Grid tied. Grid tied is photovoltaic panels, your solar panels, collect the solar energy and convert it into electricity. The basic components for this is you have the solar cell that converts the sunlight to DC electricity. You have the inverter that converts the DC energy to AC energy that powers the home. You have an AC circuit breaker panel, and then you have an electric meter. The power is either routed to the utility company or to the house, and the connection so that excess energy can be routed to the local utility grid. So basically, what we're talking about when it's grid tied is when the sun is shining, that structure can use the energy at that time, but it has no way to store that energy. So if you're using 50% of the energy that you're actually collecting, that additional 50% will go to the main utility grid, to your municipal utility company, and essentially you're going to use them as your battery. So they're going to take that and they're going to use that energy for other people, and you get a credit for it. So they're paying you for your energy. Now, you've had too many cloudy days in a row, or it's cloudy, or it's nighttime. At night, you're not producing any energy, are you? So unless you're okay with sitting around in the dark with no air conditioning and no refrigerator, that's when you're happy to be tied to the grid, because now you can pull that energy back out of the grid. So either you will pull it back as free, usually a small cost for using them as your backup storage. And then here's the one, if you're actually going to be using more energy at night than you were able to collect, you can buy the extra. So you will have continuous, easy, you can't even tell that this is what you have. So that's why a lot of people, when they do their first toe in the water with solar, they do a grid tied system. The complete opposite of that is off grid. And off grid is possible, but you have to be very mindful. Your client has to be very mindful. It's the same concept. You have a PV array, generates DC electricity. Now that usually goes through a charge controller, which is some kind of a throttle device. And that will go first into your battery bank, because your batteries use direct current energy. So First, you're going to charge up all those batteries, and then it's going to go through the inverter and be used in the house. Now, a lot of people do this also might incorporate a power backup generator as an additional backup energy source that can charge the batteries as well as supply electricity to the house. Now, whether those are propane or gas, natural gas or diesel or unleaded gas, there's a variety of those to supplement for them. And so this is you have to be very, very careful with these because too many cloudy days or you run out of gas for the backup generator, you're done. Now, what a lot of people are looking at now for a newer solar system is grid tied with storage. This is the optimal design if you're trying to achieve resilient design because it is the most flexible. It allows homeowners to produce their own electricity. Then they can send some of it back to the utility company so they can draw on the larger utility company grid when they need it. But it gives you that feeling of that seamless energy consumption. But by adding some form of on-site energy storage, usually in the form of batteries, the owners can then produce their own electricity, store some, and then use some that they send back to the utility company. So if there is ever an event where there is an interruption in the centralized power, this is the most resilient design because if the utilities are knocked out, this type of system is going to allow the homeowners to produce solar when the sun is shining, but also to have at least a nominal amount of power when the sun is not shining, like at night or if it starts to rain. So you have the ease of the utility company as your backup, you have the security of energy independence, and you have the flexible resilience of some on-site storage. Now, to show you where technology is going, this is a huge area for researchers, this idea of free energy. And so there's even research going on that they're trying to create a paint that would essentially be the solar collector. So what they have figured out how to do is particleize photovoltaic cells and mix them into paint. And so getting solar energy could soon be as simple as painting the structure and hooking up a couple of wires so that you can get that DC current off of the structure there. And so I've actually talked to the researchers that are working on this, and they say the technology works great. Unfortunately, their paint keeps peeling, so they brought a chemist in to help them with that one. So we do live in some pretty exciting times, what's becoming possible. Now, there are some interesting community approaches to meet net zero, where production-built developments have energy production incorporated into the entire area. This image is a picture of the Pecan Street development here in Austin, Texas, and it has the highest concentration of solar homes in the United States. There are over 200 homes. All have a smart meter to track real-time energy use in the house and also what is produced on the panels. The residents of this area can sell their extra power to the utility company, and their carbon emissions for this area, this regular production-built planned community section, are 60% less than the rest of the city of Austin. Now imagine if all production developments used 60% less energy. That is a game changer. Now we also have solar thermal. Now this is different from solar photovoltaic PV systems, which generate electricity rather than heat. Solar thermal technology uses the sun's energy rather than fossil fuels to generate low-cost, environmentally friendly thermal energy. This energy is used to heat water or other fluids and can also power solar heating and cooling systems. So notice the panels for this don't necessarily have to be roof mounted, which could make them more resilient in areas where you have things like hail. And solar space heating. So solar space heating systems are similar to solar water heating systems, but they generally involve more solar collectors, larger storage units, and a more sophisticated design. You also have solar cooling systems, and there's two kinds of solar cooling systems, ones that use a desiccant system and the absorption chiller systems. In a desiccant system, the air passes over a common desiccant or drying material like silica gel to draw the moisture from the air and make the air more comfortable because humidity will make it feel a lot hotter than it is. And if you live in Florida, you know that one. The desiccant is regenerated by using solar heat to then dry it back out. Absorption chiller systems use the most common solar cooling system. It uses solar water heating collectors and a thermal chemical absorption process to produce air conditioning without using electricity. So the process is nearly identical to that of a refrigerator, only you're not using a compressor. Instead, the absorption cycle is driven by heated fluid from the solar collector. So a solar hot water heater, after your HVAC system, water heating makes up the largest single energy demand in a building. Using a solar water heater is a cost-effective method of heating water. There's two types of solar water heating systems. You have an active system, which uses an electric pump to circulate the water, and you have a passive system, which uses thermodynamics to move the water. An active solar water heating system, that's the most common in the United States, both for residential and commercial applications. Solar water heaters composed of three main elements. That's it. It's easy. You have a solar collector, you have insulated piping, and you have a hot water storage tank. The electronic controls can also be included, as well as freeze protection if you're in a colder climate. Solar radiation hits the solar collector. The solar collector absorbs the heat and transfers it to potable water in the system, flowing out of the collector into the hot water tank. And then the heated water is available and used on demand. So it's simply using the sun to heat the water. Now, one of the best applications for this on a big scale is a solar thermal pool. Take a look at that awning structure on the back end there. See all the panels on the top? These are not photovoltaic panels. These are solar thermal heating panels. And so, for example, on a swimming pool, to heat a competition-sized outdoor pool located in a warm climate, I'm not talking cold climate, a warm climate, is equivalent to the annual natural gas consumption of approximately 150 single-family homes. Wow. If you can do that with solar thermal, it's free. And so a lot of hotels, resorts, apartment complexes, health clubs, and schools are using solar pool heating as a much more efficient method. Now, wind energy is using a wind power turbine to generate electricity. They can either be grid tied or off grid, just like solar panels. But here's the deal. For a home wind turbine to be worth the investment, you have to live on at least an acre or more. That's the guideline from the U.S. Department of Energy for their Guide to Small Wind Electric Systems, a wonderful free publication. Now, on average, a typical American home would require a small turbine with a minimum 5 kilowatt hour generating capacity to meet all of its electrical needs. A turbine of this size has a diameter of approximately 18 feet, the exact size needed to power a home. However, can range from 2 kilowatts to 10 kilowatts. So you're looking at a wind turbine that is 12 to 25 foot in diameter based on what that average home uses for its energy. Additionally, you're more likely to find a high average wind speed in wide open spaces far from windbreaks like buildings and trees that you're going to have in a more congested area. So unless you have a very large lot and a very friendly or no HOA, homeowners association, these are very difficult to incorporate in denser areas. As they're designed to catch wind, they're not necessarily the most resilient choice if you have high wind events or you have intermittent wind patterns. So in situations where you're using wind, it's generally combined with solar photovoltaics to help make the overall system more stable and efficient. Now, solar thermal will heat and cool. Solar photovoltaic will heat and cool. But the more efficient method to use is geothermal to heat and cool and provide hot water, and to use the solar photovoltaics to run the equipment and the motors for the geothermal system. With this type of combination, you are actually burning zero fossil fuels to heat and cool a home and even run the water heater. Considering that those functions typically consume 55 to 70% of a home's energy consumption, you can see why this is fantastic. So geothermal is heat that is generated within the earth. Geo means earth and thermal means heat in Greek, if you look at the root language. This is a renewable resource that can be harvested for human use. Now, when it comes to heating and cooling a space, geothermal is actually the most efficient method of heating and cooling and is more than 3 times as efficient as the most efficient conventional system. And it's much more energy efficient than trying to use standard HVAC systems that are you're powering with solar or wind and a gas furnace. Geothermal HVAC systems remove 4 times more kilowatt hours of consumption from the electric grid per dollar spent than a photovoltaic or wind power add to the electric grid. So those other technologies can certainly play an important role, but the geothermal HVAC is often the most cost-effective way to reduce the environmental impact of conditioning spaces, and they are incredibly long-lasting. The earth loops that you use for this are made from high-density polyethylene or polybutylene pipe. They can last for generations. The heat exchange equipment typically lasts decades since it is protected inside, out of the weather. It doesn't need to be replaced. The expense is a lot less than putting in a whole new geothermal system because the loop is the pricey part to install. Once you've got the loop in the ground, that heat exchange equipment lasts very, very, very long time, and you can just replace that. The new technical guidelines eliminate the issue of thermal retention in the ground, so the heat can be exchanged with it indefinitely. In the past, some improperly sized systems did not, they overheat or overcool the ground over time to the point that the system couldn't function. You have to have enough change in temperature grade to allow this process to happen. So when you have multiple systems, a geothermal system can heat the water, can heat the pool, can heat and cool the home, and can also be used in radiant flooring to heat the floors in the house all at the same time. Now, geothermal systems use a heat pump for the HVAC system. So first things first, what is a heat pump? I like to start with the easy question. It is exactly like what it sounds. A heat pump moves heat from one place to another rather than creating heat or cooling by burning a fossil fuel like a furnace or a boiler. And I do this by taking advantage of the fact that liquid refrigerants absorb huge amounts of heat when they turn into a gas and go into evaporation. And it releases that same heat when they're condensed back into liquids. So the most common kind of heat pump, called an air source heat pump, uses the energy in outdoor air to heat and cool. To cool a warm space, a heat pump evaporates the liquid refrigerant in the copper coils indoors and condenses it by a compressor in similar coils outdoors. To heat a cold room, a valve is activated that reverses the process. The gaseous refrigerant is condensed indoors, where it gives off the heat, and it evaporates in the outdoor coils, picking up heat from the outdoors in the process. So air conditioners and refrigerators use the same exact process to deliver the cooling performance. Why are they such great heating and cooling options? For one, heat pumps can be incredibly efficient because they move rather than create heat. They can often deliver 3 to 4 times more energy into your home than you use to power the heat pump. So very high efficiency air conditioners might get the same benefit. Unlike those air conditioners, heat pumps also provide both heating and cooling, meaning you don't need 2 separate systems that only get used for half the year. So with all these benefits, you might expect to see air source heat pumps everywhere, but you don't. What's the catch? Well, because they are more complicated than typical air conditioners and furnaces, and they're a bit more expensive up front. And they work best in relatively moderate and humid climates. The greater the difference between indoor and outdoor temperature, the harder they have to work. Once outdoor temperatures drop below 40 degrees or so, heat pumps are not that efficient as heaters, and you need some kind of auxiliary heating. In very, very hot climates with low heating needs, air source heat pumps are no more efficient than air conditioners, but they're more expensive. So fortunately, there's a great way around those limitations on traditional air source heat pumps. In even the most extreme climate regions, the temperature several feet underground is between 45 and 75 degrees Fahrenheit. Enter the geothermal heat pump, also called a geo-exchange. And these electrically powered devices could be solar electric energy powered devices, circulate a fluid through piping buried in the ground. or discharging the heat to the ground in the summer and pulling it from the ground in winter. The heat pump coils are in contact with this fluid rather than the outside air, as in a standard heat pump. Therefore, they avoid that huge temperature swing in the air temperature. So geothermal heat pumps can be incredibly efficient, delivering 3 to 6 times the amount of energy used to just power the pump's compressor and fans and pumps. You can easily power those with solar power, and the systems run very quietly. There is no equipment outside, so no noise outside at all. So that traditional sound of summer of the air compressor on everybody's house, that thunk, hung, you don't hear that anymore. And since there's no equipment exposed to the elements, they last a lot longer. So it's that very, very easy thing during the heating process. You're pulling the heat from the earth, and you're bringing that in, and then that's being circulated through the house. So the heat energy is transferred to the geothermal unit. The unit compresses that extracted heat to a high temperature and delivers it into the home through a duct system, regular old duct system or a radiant heat system. Now for cooling, you just reverse it. Because the earth is much cooler than the air temperature on a hot day, the geothermal system removes the heat from the home and deposits it in the ground. The fluid is cooled by the ground temperature and returned to the unit for cooling the home. Energy efficiency comparisons. Energy Star rated electric central air conditioner has a minimum 15 SEER or 12 EER. EER is the energy efficient rating in the cooling mode, represents the ratio of total cooling capacity to the electric energy input. Geothermal heat pumps have an EER from 15.5 to 37. They're that much more efficient. So controlling all of that can be incredibly cost effective. Now, there's a lot of different options for installing a ground source heat pump. You have closed loop and you have open loop. Now, closed loop is the more typical one that you're going to find. You have closed loop horizontal, where they do a series of trenches, typically 4 to 6 feet deep, 400 feet long, and then you coil that tubing up within those. Here's an image of a house that they've got the trenches dug, and you can see how the coils are laid in the bases of the trenches so that you can optimize that temperature exchange there. You can lay the loops flat, or they can lay them on their side. The other type is a vertical loop. Now, this is where you have maybe a smaller property or you've got to go deeper down. And so pipes are inserted vertically into these holes that have been bored into the ground, usually by some kind of well drilling equipment. Holes could be 75 to 400 feet deep. Typically, they're about 125 to 150 feet per ton of heat pump capacity, and you could have multiple vertical shafts. Now, when you get closed loop, you can also do a pond or a lake that if you've got water nearby, this is a closed loop system. The fluid inside the tubing never leaves the tubing, and the fluid around it never comes into the tubing. And so you can actually use the water, the surrounding water, to cool that fluid in the tubing. Now, open loop, the fluid in the tubing is actually exchanging out. So you could have it in a deep well hole where you're pumping water in and then you're pumping water out elsewhere, or with a lake. Open loop is a little bit more challenging. Closed loop is the more efficient, typically more easily found. Now, to give you an idea of cost, you might think, wow, these must be hugely expensive. Well, check into a lot of the federal and local incentives. They had been running on almost 30 to 60% of your total geothermal cost, which can make a huge difference. A standard air source HVAC system costs about, give or take nationally, about $3,000 per ton for heating and cooling capacity during new construction homes. Some of the new construction homes out there, they're anywhere from 1 to 5 tons. Geothermal systems start at about 5,000 per ton and can go as high as 8 or 9,000 per ton, depending on the installation method required. However, new installation practices are getting better and reducing the cost to the point where the price is getting closer to conventional systems. Factor that you have basically reduced the costs of any kind of further energy. And then we're getting to the point that there are production builders now that are building entire developments with geothermal, takes advantage of the economies of scale for the community, and it actually comes in almost less than a standard conventional system. So if this becomes a standard or practice, you're actually going to be getting cheaper and then have infinite low cost energy. Great. So why are we not using it yet? Isn't that a great question? Now, in addition to all those cost benefits, you also have some other environmental benefits, and one is that noise. When you're dealing with all the HVAC systems, either in a residential development or especially in a commercial cooling tower systems, you're talking about a lot of noise, and commercial cooling tower systems, an enormous amount of fresh water gets wasted. So there are tremendous benefits on all sides. If you're working on a project now that's a new project, even a commercial project, you may want to consider investing a little time in researching if this is a good method for your client. Geothermal also has the benefit that no equipment is outside. So all those people that are having their air conditioning units stolen for the copper coils, or that are being flooded if there's any kind of a weather event. In fact, in Florida, for government buildings, hurricane hardened shelters are required to house the outside equipment. Those enclosures could be as large as a gymnasium and can cost millions more. So in that case, a geothermal system is actually cheaper than a standard system. And even if the house blows away with these kinds of closed loop systems, the geothermal is intact. Just hook up a new geothermal pump, because your geothermal pump may be gone, put a solar photovoltaic panel out there to power the motor, and you're in business. You could actually have the coolest tent in the neighborhood after one of these. So why not geothermal? It's resilient, it's energy efficient, it's quiet, it's cost effective, especially if you have any rebates or take advantage of doing a number of houses close together or buildings close together for economy of scale. You have a low carbon emission. You have no carbon emission if it's powered using solar photovoltaic panels, and it's incredibly long lasting. And when you compare it to a commercial cooling tower, you also save all of the energy on that. So again, there's all different ways to get to net zero energy. It is going to be coming. We are not seeing a huge drop in fossil fuels. Coal is finite, oil is finite, and we don't have control over them. They can be turned off if we can't get the supplies on them. So this just makes sense from a practical viewpoint. You may not be able to go fully net zero, but you definitely can go into at least a little bit of the application and mix some in. So I like to leave you with a little bit of humor. What do you call a massive solar energy spill? A nice day. I hope you've enjoyed this class. I hope you've got some good information out of it that you can apply to your business. And I look forward to having you back again with some of our other Design Art Seminars CEU courses, whether it's in person or through a webinar or through a live webinar. Please join us for your future CEU needs. If you have any questions, don't hesitate to reach out and let me know. Thanks so much.